Hello everyone, I'm Ankit Naik, Applications Engineer at Wolfram Mathco, and I'm joined by my colleague Sergio, one of our software developers. Together, we will walk you through how System Modeler can be used not just to simulate systems, but to actually train AI models safely, explainably, and efficiently, using simulation as the learning environment. In the next 20 minutes, we will show you how your existing models can become powerful data engines for predictive, surrogate, and reinforcement learning workflows. Before we look at the workflows, let's take a step back and ask, why should we train AI with simulations in the first place? We think there are three key reasons. First, we want to use AI to make decisions, but those decisions should not be opaque. With physics-based models, every action the AI takes can be traced back to real equations and first principles. This explainability is essential when we are building safety-critical systems, for example in automotive, aerospace, or energy applications. Second, collecting data through experiments, especially to model corner cases, can be risky or even impossible. Think about testing material behavior near its melting point or high pressure conditions in a submarine. Simulation lets us explore those extremes safely and systematically. Third, physical experiments are expensive and slow. Setting up rigs, running tests, and labeling data takes time, labor, and equipment. Simulations lets us generate vast, labeled datasets quickly and reproducibly. There are other advantages too, like scalability and easy integration, but these three really capture why simulation is such a powerful foundation for training AI or ML models. Simulation is to AI what a test bench is to hardware, a safe, controlled space to prototype intelligence before deployment. In today's session, we want to share 3 AI plus simulation workflows that we have seen some of our users successfully applying. By the way, when I say AI here, I really mean machine learning systems. These are just a small selection from the many things you can do with System Modeler and Wolfram language, but we think they give a good balance of breadth and depth. We will start simple by training a neural predictor for future state or health estimation. Then we will look at how to build surrogate models for fast design exploration, which is especially valuable for optimization. Finally, we will end up with a quick glimpse into reinforcement learning, where an agent learns control logic directly through simulation. Each of these topics could easily be a presentation on its own, so our goal today is to give you an overview, to show the workflow, highlight results, and let you see the power without diving too deep into every line of the code. Let's start with our first workflow, using a neural network to predict future system states. This is like building a fast numerical estimator, similar in spirit to a Kalman filter, but learned from data rather than derived from equations. This idea has many use cases, like estimating battery health, predicting temperature inside a building, or anticipating thermal behavior in chemical process plants. For example, in an electric vehicle, you may have only a few measurable signals like voltage and current, and you want to predict the battery's state of charge 10 seconds into the future. Traditionally, model predictive control relies on linearized version of the physics model for fast prediction. But instead of linearizing, we can train a neural network to approximate the same predictive behavior, which is especially valuable when the underlying physics are nonlinear or when fast computation is required. So, if MPC traditionally uses a linear approximation of the plant, this approach simply replaces that small signal model with a learned nonlinear one. We recently concluded a consulting project with a major truck manufacturer where this idea was explored, that is, using a trained neural network inside a model predictive control loop. I can't share all the details, but conceptually the goal was simple. Given current system states, predict the future temperature or performance so that corrective action can be taken early. For this demonstration, let's revisit a model some of you may have seen in my thermal management of EVs talk. Here, it's a simple battery cooling circuit with a pump, a liquid to air radiator, and two valves controlling flow between the radiator and the battery loop. Our goal here is to predict the battery temperature 100 seconds into the future, given the current battery temperature and the states of the two valve openings. We simulate about 350 different scenarios by varying those parameters. Each simulation produces input-output data pairs that we can use to train our neural net. We launch all the simulations in parallel using system model simulate function, then prepare the data set using the simulation results. We can then create our custom neural net and then train using nettrain in Wolfram language. After training, we get a neural net that takes three inputs: two valve positions and current battery temperature, and outputs the predicted battery temperature 100 seconds later. We can even embed this trained network back into System Modeler as a component and compare its prediction to the real physics model. Here are the results after 100 seconds. The yellow bars show the actual battery temperature and the blue bars show the predicted battery temperature. As you can see, the predictions are quite close, showing that the neural network has learned the system dynamics well enough for predictive use. This network can now be integrated into a control loop or used as a fast onboard predictor. Of course, we also need guardrails to monitor and verify its behavior. What we have now is a network that predicts a single future value for a particular time horizon like 100 seconds. You can think of it as a compact surrogate for the model's short-term dynamics, accurate enough for controlled decisions but light enough for real-time use. But what if we want to mimic the entire dynamic behavior of the system and not just one snapshot? That's where surrogate modeling comes in. In engineering applications, two very common tasks are optimization and calibration. Typically, we start with a physics-based model, collect some experimental data, and then adjust model parameters so that simulation results match reality. Or we may define a performance or reward function, for example, to minimize energy consumption, and want to find the optimal design or control strategy. Doing this directly on the full physics model can be time consuming, especially if the initial parameter guesses are poor or the system is highly nonlinear and prone to local minima. This is where a surrogate model becomes useful, which is a fast neural representation of the system that approximates the physics model closely enough to guide optimization. The surrogate here plays the same role as a reduced order model in CFD. It preserves behavior over the region of interest but runs dramatically faster. Let's look at an example. Here we will be using one of our upcoming functions called system model surrogate train to create the neural surrogate. The surrogate architecture we are using is a continuous time echo state network or CTESN a kind of recurrent neural network designed to learn time series dynamics directly from simulation data. The workflow is simple. We specify which output variables we want the surrogate to predict and define which parameters you want to vary and the range of your design space. In our example, we ask the surrogate to predict battery temperature and power consumption for different values of cell internal resistance, a parameter representing different battery types available on the market. Using the new function, System Model Surrogate Train, we automatically run about 200 simulations across the design space and train the neural network surrogate to reproduce the full time series behavior. Once training is done, we can extract parametric functions for each variable, for example, one for temperature and one for power. Then we compare the time series results of the surrogate and the original physics model for a given parameter value. The curves overlap closely, meaning the surrogate successfully captures the underlying dynamics. We can also compute the root mean squared error across all parameter values. Here you see the differences are small, which gives us confidence to use the surrogate for faster analysis and optimization. Because the surrogate runs orders of magnitude faster, we can use it inside optimization routines, such as integrate power over time to compute energy, define a custom reward function, and quickly scan the design space to find the best configuration. Finally, we can even convert the surrogate into a system modeler component. This allows us to combine neural network based components with physics based models, creating hybrid systems that run faster but retain physical structure. A practical use case of the surrogate model is also cloud deployment. You can let end users interact with your model, run parameter sweeps or optimization without exposing the underlying intellectual property. This approach is especially useful when you need fast evaluation in the cloud or an embedded hardware. So far, our networks have been trained to predict or approximate system behavior. But what if we want the AI to go one step further, to make decisions on its own by trial and error? That's where reinforcement learning comes in. For our final demonstration, let's look at a simple reinforcement learning example. The electric kettle. It's an intuitive system where we can easily understand what's happening. The kettle heats water, and the agent's job is to decide whether the heater should be on or off at each moment. Reinforcement learning here is comparable to tuning a controller by simulation rather than by hand. The agent iteratively finds gain settings that satisfy the reward. In reinforcement learning, an agent interacts with an environment, and here the environment is our system modeler kettle model. The agent takes an action, observes the state, which could be the water temperature, and receives a reward or penalty based on how good that action was. There are many reinforcement learning algorithms, but today we will use one of the simplest and most classical one, which is called Q-learning. Here, the agent stores what it learns in a cheat sheet called a Q table, which records how good each action is for every possible state. At first, it explores randomly, which is called epsilon greedy policy, and over time, as it collects experience, it gradually shifts from exploring to exploiting what it has learned. Here, training happens over many episodes. and each episode starts at a random water temperature. The agent can take up to 50 steps, choosing whether to heat on or heat off. After each step, it receives a reward: negative when it moves away from the target, and positive when it moves towards it, and highly positive when the temperature is just right. Let's look at the learned policy. In the beginning, the Q table is mostly empty. The agent doesn't know much. As training progresses, the table fills in. Temperatures below about 350 Kelvin show negative rewards for turning heating off, meaning keep heating, while temperature above 360 Kelvin show positive rewards for turning it off. Eventually, the agent learns a clear policy: heat until the water reaches the target range, then stop. We can then export this learned Q table as a lookup table in System Modeler and plug it back into the kettle model as a controller. The final Q table is effectively a data-driven lookup controller, similar in spirit to what many of you may have implemented empirically. When we test it for different starting temperatures, the controller consistently brings the water to the desired range and keeps it there, all learned automatically through simulation. So in this last workflow, the AI didn't just predict or approximate, it learned to control a system entirely through simulation. To summarize, we have seen three different ways you can train AI using simulation in System Modeler and Wolfram language. First, we build a neural predictor to estimate future states, showing how a trained network can forecast what happens next in a system, just like predicting the future battery temperature in an electric vehicle. Second, we used surrogate modeling to accelerate optimization and calibration, replacing a detailed physics model with a fast neural surrogate that runs in milliseconds while maintaining physical realism. And finally, we explored reinforcement learning, where a controller learns its own policy directly from the simulation environment, safely making mistakes and improving over time. So, across all three workflows, simulation served the same role as it always does is in engineering: a safe, repeatable environment to design, tune, and verify before deployment. Together, these workflows show how simulation becomes the data engine for AI, enabling explainable, safe, and efficient learning across design, optimization, and control. That brings us to the end of our presentation. Train your AI with System Modeler. We have seen how simulations can help train neural predictors, build surrogates for optimization, and even let controllers learn autonomously through reinforcement learning. Now, let's open the floor for questions. Thank you.
All right. I guess now we can look at the questions. So we have one, it says, how do you connect your estimator to the system modeler model? So there are a couple of, fundamentally we use one function, which is create system model. So what we showed in the presentation is that once Ankit finished training the neural network, you can just pass it directly to this function to create system model. And this is gonna automatically create a system modeler model that you can directly connect with all your other components. And then in the case of the surrogate, when you train the surrogate model, you can just ask for the property system model. And then this one automatically produces a system modeler model. Then again, you can just connect with the rest of your components. But I see that you have a different second question, which is that why is your estimator only predictive learning according to a simulation batch and not an online estimator learning during the simulation? Right, you're right. I mean, this is another possible workflow in which you would like to have something that, like an MPC, automatically updates its state and predicts according to what the simulation is currently doing. I think it's an interesting approach. I think we haven't really done something like that right at the moment, but it's something that we definitely want to look into. Actually, I can actually share the screen and maybe show you a little bit of how this happens. So in the case of the presentation, when you went the neural network, so what Anki did was, yes, so once he was done training the neural network, which is this one, all he did was taking this fnet and he passed it to the function create system model. The other things that he specified is the model name that you want to use for the neural network. And because we need to export the neural network in some format, we use ONNX. So just like a file location where you want to put this ONNX file. And then you just run that and automatically create system model is going to create a system model from that neural network. And this is now just a component that you can connect with the rest. So here is the result once you have taken the neural network that you created, this one, mainnet, and then you can just connect it with the other stuff in your models. And then in the case of the surrogates, I can show you. Okay, actually we have also here, maybe I can show you here in a different example. So here I was training a different surrogate model. This is for a model of satellite that we have in System Modeler. So you can already get it automatically. And I'm just, in this particular model, we deploy a satellite to a certain altitude. The idea is to use the surrogate. In this case, we are going to use one of the controllers in the satellite deployment system to create the surrogate, to explore this parameter space of this controller, and then just to see how the position of the satellite behaves. So we train the surrogate. Here we see how the distance, how the height of the satellite behaves for different values of the parameter. And then I can just extract from the surrogate, I can just say one of the properties that it has is neural net. Then you get the neural network corresponding to the surrogate. Or you can just say system model. And then this is going to create a system model corresponding to the surrogate. That you can just take that and connect it to either to your original model or to other components in your system modeler environment. So we can just open this. As you can see, here is hidden all the information that is in the surrogate. You can simulate it. And because it's a surrogate, now this simulates very fast, and you can explore all the parameter space in system modeler now that you created a system model from your surrogate. Right. Let me see the questions again. Is it possible to modify the neural net weights during the simulation? During the simulation for the neural network case, so for the neural network that you have already exported into simulations into system modeler, the information that of the neural network is now stored in the ONNX file. So that's a little bit harder to dig up and modify. But in the case of the surrogate, a lot of these parameters in the surrogate are actually stored in just very simple comma-separated value files. So you can just dig them up and modify them if you want. But to modify it into during simulation, I don't think you could do that at the moment, unfortunately. But yes, this I guess this goes again in the spirit of like automatically training in simulation, which would be an interesting approach that we haven't really explored. But yes, this is worth discussing for sure. Okay, maybe while other questions arise, I can show you something else that with this example of the satellite. So in this case of the satellite, as we mentioned for the surrogates, we want to focus on optimization. And one thing that you could, for instance, ask in the case of your satellite that is being deployed is you probably want to reduce these oscillations of the satellite once it reaches the final height. So you can create like a function that quantifies those oscillations and then try to minimize those oscillations with in your surrogate. So for instance, here I'm just doing a couple of integrations, numeric integrations here to compute these oscillations for different values of the parameter. And in this particular case, you get a very nice curve that you can easily minimize. So you can find the ideal value of your parameter in the parameter space that is going to produce the least amount of oscillations in the final height of your satellite. So this space of optimization problems that we want to explore for system models is something that we definitely want to cover in more depth in future releases, probably something like a function that would automatically do the optimization for you. But for now, yeah, we're just exploring the capabilities at hand. Right, something like a Kalman filter. Yes, exactly. Yes, that's indeed the point. Right. Let's wait a couple of more minutes before we stop there. And I guess there's probably no more questions for now. So hopefully you guys have found this interesting. And then I think it's next, so tomorrow we have another presentation about requirement validation. That's just me. We also have an office hours time tomorrow. And today we have an open and working session in like half an hour where I'm also going to be around in case you want to ask more questions. So I guess if that's all for today, we can leave it there. Thank you so much. And I hope you can enjoy the conference. Thank you.